Appreciate y'all staying awake. It's a long day and a lot of stuff to soak up. All right, and as I think Sean mentioned, all these slides and everything that you're seeing should now be online at chromium.org. If you drill down a couple levels, Chrome OS to, you should find the link. And apparently we'll have video at one point before too long. All right, so I'm Bill Richardson. I've been with Chrome and Google for 4 years now, and I'm going to talk about the embedded controller. So our embedded controller, first of all, like most of this stuff, is open source, so you can go look at it. We did our own EC because we just had problems with the legacy ECs. It was a long process we'd find a change that needed to be made, we'd put in a request, a couple days later they would say, what? And then we'd explain, we'd put in another request, and then a couple days later we'd get an image that fixed that bug and introduced a new one. And that was kind of a pain. And we also ran into some issues with boot speeds. Some of the ODM ECs had, delay loops in there to account for weirdnesses with Windows 95, which we didn't really need. Things like that, as well as security. And security was primarily one of the factors that we were concerned with. So just like the firmware, Chrome OS EC has both read-only and read-write parts. The read-only part is hardware read-only as near as we can make it. There's a few caveats there, but it is effectively read-only. And then the read-write part is signed by Google, verified, checked, made sure it's all correct as part of the boot process. And so the whole EC read-write is part of software sync. Is part of the verified boot process. We currently have two ARM-based SoCs that we use for embedded control. We have the TI Cortex M4 version Blizzard, which is their code name for it. I think it's called LM4, or maybe now TM4 is the new name. And then we have an STM32 from STMicro as well. We're looking at a couple of others in progress to just see, can we have other parts, different pricing, so forth. So that's underway. The source tree is laid out. It's in the source platform EC branch of the entire Chrome build system. And much like depth charge and core boot, it's laid out into various directories. There's a board specific area which pertains to particular Chrome OS devices, Chromebooks. There's a chip specific area which is which system on a chip is this EC actually made from. And then we have a bunch of common stuff, obviously, for different modules and things. Core functionality for task switching, drivers for various peripherals that are common. Power sequencing logic, this refers to powering the AP, that is the host CPU, not the embedded controller itself. A test directory and some utilities that just are handy. And when you build it, everything is dumped under a build directory in a board-specific subdirectory. So, clean that up from time to time. If you if you check out differently in Git and you switch to a different branch or something, still building the same board, it'll leave a lot of object files in there. You want to clear those out or the dependencies get messed up. Okay, so terminology, in case I use a few phrases that you're not familiar with. When we say AP, we mean the host, the main CPU, the ARM processor that runs the Chromebook or the x86 processor. And we called it the AP because we used to call it the CPU, and people say, wait, do you mean the EC CPU or the, no, it's that. When we talk about hibernation, the EC has a mode where it just goes to sleep, doesn't consume any power, consumes almost no power. And that's its hibernate mode. Sometimes it will wake up with a timer if we want it to. Sometimes it just sits until somebody pokes a button, but it will wake up. The ECs also support, as do most of the Chromebooks, a battery cutoff or ship mode where although everything is dead, nothing's drawing power, the battery's still actually connected. Keeps the clock running, but nobody cares. And some of our partners would like that battery to be completely off, so we usually have a way of just completely disconnecting it electrically. Not necessarily physically, but perhaps through a transistor of some sort that just, there's no power coming out the pins. Tasks in the EC, it is a multi-task, multi-threaded, semi-real-time operating system. that we wrote, and so there are several tasks of different independent execution. Of course, there's a watchdog timer on the chip, which we poke from time to time, and it will reboot if nothing seems to be happening. And then finally, we talk a lot about a Celego chip. Celego is the brand of the custom IC that we use. This is a little hardware gadget that is a "Am I Trustworthy" module. So we have a latch that as the EC boots in its read-only code, we trust it. And then when it goes to its read-write code, we still trust it because we did it. But if somebody came along and was able to somehow get an exploit and mess around with the EC, it would still be running in read-write code. And then it could lie and say, no, I'm in read-only mode. I'm really running my read-only firmware. Well, it can't lie because we've got this one-way latch. And as we leave read-only for real, we flip it. And then we can tell by looking at that GPIO from the host side, from the AP side, whether or not the EC is lying to us. Okay, so so far so good? All right. So the firmware architecture, several big pieces to the embedded controller. There are tasks, of course, which I'll talk about because you can have independent threads. The standard GPIOs and interrupts, that's mostly what the EC is about. The EC implements a number of modules, which are common functionality like, serial port out and that sort of thing. There are hooks, which are important with ways in which different tasks or different functions can be invoked in response to what state the EC is in or what it's doing. There's a console, so you get a serial debug console on the EC, which is always enabled. It's just that in a shipping system, the pins that let you get at it are inside the machine, so it's not as useful. But it's very handy for debugging purposes. We have also host commands. That is how the AP talks to the EC, tells it what it wants to do, finds out what it's doing. And finally, we'll talk a bit about the configuration of all this. So tasks. So the EC, again, it's a tiny little processor with a very limited amount of memory and so forth. It doesn't run very fast. But it typically runs between 6 and 10 independent tasks. In each of those tasks, a separate thread and all the normal CS thread sense. It has its own stack. It has, interrupt-driven task switching. So unless you've blocked interrupts some way, you don't necessarily know when your task is going to be swapped for a different one. And it has a strictly ordered list. This is somewhat different. Strictly ordered list of task priorities. So there's a highest priority task, and then every task below that is of a lesser priority. 1, 2, 3, 4, 5, 6, 7, right on down. And a higher priority task will interrupt a lower priority task whenever it feels the urge. And of course, to communicate between all those tasks and share resources, we have all the standard event, wake on event, sleep, timers, mutexes, things like that. One thing that is a little quirky or may cause some quirks, or better, may avoid some quirks in the embedded controller is there is no heap. That is, we have no malloc, no free. So when a task is running, we want it to use only the memory that it needs. We don't want it to have a leak somewhere and grow without bounds. But there are a few fixed-sized static memory buffers which can be shared around among the various tasks. So a task could say, hey, I need to do some input here, so let me grab one of those buffers, do a little calculation, then I'll give it back. And I need to give it back before I'm done. So the next task can come along and grab it again. Okay, so here's an example of some of the stuff that might go on a config file. Under the board directory, we have a number of platforms, Rambi or Link or whatever the various Chromebooks are. And then in each of those, they will have a ec.tasklist file. And this is just a header file that's mangled in special ways. And we define the various tasks. And you can see here, the lowest priority task is the first one that you see listed, which is a hook task, followed by a charger, chipset, keyboard protocol, host command, console, power button, and keyboard scanning. So in other words, keyboard scanning is the highest priority task that runs on the EC at any given time. So if I come along and tap a key on the keyboard, that will get the EC's attention more so than if I press the power button or ask it to monitor the battery charging and so forth. That said, we tend to switch tasks fairly frequently, so it's not a big deal. I don't even remember what our task frequency task switching is, but it's fairly rapid. It's on the order of several hundred hertz probably. So, okay. GPIOs, again, as you might expect, These are the normal inputs and outputs and interrupts that you would get from the main board. And so some of these things are specific to the EC and the things it's looking at, like keyboard. Others have to do with power buttons or what state the CPU is in, perhaps what state we want the CPU to be in, the AP, I mean. And so some of these may have interrupt handlers and some may just be straight interrupts, and you can see a few examples here. I've cut out some of the intervening bits. So we might want to be, driving certain power enables for the chipsets. We might want to know when a USB port is overcurrent. We might want to be interrupted when the lid is opened or somebody presses the power button or we insert the power or remove the power adapter. All right, so modules then are just a way of having some common code. Someone was asking how can we share some of this code, not duplicate effort, and this is one way. So we'll have some common modules. These are under the common subdirectory. And they handle things like A to D conversion for sampling various things, charger watching the battery charger, watching the various chipset features, memory accesses, the GPIO management itself, various bookkeeping tasks, buses, things that we need to talk over, respond to bus traffic, fans, thermal management, all this kind of stuff. And so these are modules that can control that logic function. Typically, one or more of these modules is handled by a specific task. So we may have a charger task whose only job is to keep up with the battery, but he does that by going through the charger module so that we can kind of treat all different varieties of battery chargers the same. And of course, each module has its own little state machines as needed, and those will be also tied to their own interrupts and their own GPIOs. And you'll see here is an example where we might configure some GPIOs that are used by certain modules. So in this case, we have a UART or two, we have some I2C buses that we need to maintain, maybe PECI if we're talking to x86, which we are in this case, LPC bus, so the LPC master is the AP, and he talks to the EC and says, hey, I wish your attention, and so we have to kind of monitor and respond when that happens. And in this case, this is code that uses the TI Blizzard chip for the EC. In this case, each of those GPIOs has some special alternate functions that are not normal, ins and outs. They could be used as normal ins and outs, but the actual system on a chip has special purposes for them. And here we're saying which bits of those register banks, which bits of those input banks and output banks are associated with which logical modules within the unit. And that way we can come along later and say, hey, I2C module, initialize yourself, start paying attention. And it can say, great, these are my GPIOs, those are the ones I want to use. So configuring that is a matter of looking at the schematic, just knowing what the board's doing and saying, oh, these pins go to the I2C bus on port 6. We need to make sure that we configure them properly so that we can have the EC talk to them. Okay. Hooks then are functions within the EC source code that are called. They're callbacks. You say, all right, I'm going to register a function. I want to have it called under certain circumstances. And that might be when something happens, like somebody pokes the power button or the AP is turning off or turning on. Or it may be invoked when some delay. I may say, okay, call me again in 10 seconds and make sure that everything is shut down properly. Or I want to be called every second so that I can be sure that nothing's overheated. Often, though, these hooks are registered by one module. Say, I may want to register the thermal in the thermal loop, but I want to be called by something else, maybe when I get a power event or battery charging. So because these callbacks are actually triggered from one task but registered perhaps by another, it's very easy to get into a deadlock state, and you need to be cautious about that. When you call if you gather any resources, if you lock any particular resources in a callback, you need to make sure to let it go before you return, or before it could be interrupted. So that's another point to be considered. But if you read through the header file where it talks about the hook functions, include/hooks.h, there's all kinds of warnings and explanations of this. It's really not that hard. And we have a number of different hooks that are called or used throughout the source tree. Obviously in init, when everything's coming up, I need to turn certain things on. We have the ability to change the frequency on some systems so that we can conserve power. If we're going to go to sleep, if the AP is in an idle state or suspended, we can say, you know, there's not a lot for me to do. I'm going to throttle myself down to a low frequency. When it comes back, I might need to scan the keyboard quickly and be responsive, so I'll boost back up at the you know, consuming more power. We have hooks when we're getting ready to switch between read-only mode, read-only firmware, and read-write firmware in case we want to prepare ourselves in some way. Various initialization, startup, resume hooks for the chipset when, you know, board power comes up and down, or the power state, lid states, things like that. So we can let us know when these events have occurred, as well as a, you know, periodic continual tick or a longer tick of a second or so. So these are the sort of hooks that we'll see, and these sorts of things happen throughout the EC. Okay, so how do you keep track of all that? We've got tasks running, we've got functions calling each other, we've got stuff talking back and forth, we have events being delivered, interrupts occurring. What the heck's going on? Well, as I mentioned, there is a serial console, and there's a task devoted to that serial console, and his job, or its job, is to give us a nice, pretty command line interface. And so we have a servo board, a debug board most of you have seen, I hope. Connect through that, and then we can get a good look at the serial console. We can issue commands, we can talk to the EC while it's running, check the GPIOs, and it will also print a ton of debug messages, which we can turn off and on in terms of modules that are printing or in terms of priority, things like that. And it's really easy to add a console command. We think we have all that we need right now, but one thing I found very handy when I'm debugging is always, always, always I will have the serial console up and watching, because otherwise I have no idea what's going on. And if something weird is happening and I don't have a function that will tell me what it is, it's really easy just to add one. You just define a function that takes the standard argc, argv arguments, just like any other main function would in C. Say, hey, this is going to be a console command, give it a pointer to the function, and when you type the command, it invokes with whatever args that you want. And so you can poke around, do all kinds of stuff. And it's not at all unusual for me just to write a couple of one-off console commands, load that image up, and then I can have it run tests or do things repeatedly, and then, you know, take it back out before I'm done. Okay. So some of the built-in commands, I called this up yesterday and just said, what do you know? And these are the sorts of commands that you might find enabled on an x86 system. You'll get very similar ones on ARM. There's a great deal of overlap. It's, you know, some peculiarities perhaps for various peripherals. But this is the sort of thing that you might see. You can turn the AP off, you can slow it down, you can send it events, you can query the chargers, you can, you know, tell the charger to provide a certain amount of current, examine every kind of thing, including flashing the chip and erasing stuff and reading memory directly from the EC in the EC's memory space or memory mapped I/O space. There's I/O commands. You can look at all the GPIOs. Again, pretty much anything that you want to know that the EC's doing, it has a command and there's a little help, and it will help you out. That's very handy. Host commands is another important task that needs to be dealt with, and this is how the AP communicates to the EC and back. And the idea is the EC is sitting along, managing everything, doing what it can, and then the AP may say, hey, I want you to tell me something here. I want you to know, let me know what's going on. So it will send a command and some data along to the EC. The EC processes it, replies with a result, true, false, it succeeded or not, or perhaps an error code, and then maybe some data back. And the data in either direction can be 0 up to some fairly large limit, like 500 bytes or so. And so this is all clearly defined, and there are lots and lots of these types of commands. There are things like control the fans, or turn the lights off, or shut me down, or just the normal, what keyboard, you said somebody was typing on the keyboard, I don't want to hear that anymore, turn it off. Or basically anything that you can get with a console command, you can also get through the host command, although there are fewer and perhaps less flexible host command than console commands. But these are very important, and this is just the sorts of things that happen. Some of these host commands, for example, will come in response to ACPI event handlers. So the EC notices that something's getting hot, it sends an ACPI event to, or SCI I guess it's called, to the AP, the AP says, what's hot? Queries the EC comes back with a big list of temperatures and things, and then it moves on from there. And so there are two channels. There's one for the kernel to use in terms of this kind of stuff, and a different one for user space to use. So we can have two channels communicating with the EC at once, and they don't interfere. They actually take turns. Even if they're on the same bus, they have different logical ports. Sometimes it's handy for the AP just to know what the EC is doing without specifically asking it all the time. And on some systems, notably those x86 systems with LPC bus, there's some shared memory regions where just in the LPC bus address space is a region of half a K or so of memory locations. And what happens is, from the AP's perspective, these are read-only, the EC then just updates them constantly with some values that it has. For example, battery voltage, fan speeds, ambient light sensor data, things like that. Those are well defined. If a system does not have a shared memory access like this, there are the equivalent host commands to access them. It's just faster and easier to not clutter up the bus if all you're going to do is be reading these things constantly. It's a handy feature. Okay, finally, we've got all these features. These are all the things that the EC can do, and this is a kind of a view from the top of what pieces of code go about doing them. How do you turn it all off and on? Well, there is a config option for most of these major features. If I have an ambient light sensor, I'll have a config underscore ALS, blah, 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 telling me which one it is. I might have a config charger to tell me which type of battery charger I have, because there's several. I'll have other config options as well, and I could turn them off and on. And then in each board's specific directory, where we customize this per Chromebook, we'll have a header file and a C file that define these config options appropriately and set up the tables that those modules expect to see. So for example, in one of the header files, you might see something like this. Here's one that says, all right, I have a backlight and I know it's tied to some pin. I have a smart battery. I want to be able to read what version of firmware board I have using some dedicated GPIOs. I do have a charger. It's a BQ24738 type. I want to be able to allow the charger to discharge even when it's on AC. If I tell it to, the chipset can throttle, this kind of stuff. It's a Haswell chipset, for example. How do I speak to the keyboard? Where do I have the right kind of power buttons? You see what we're at here. So these are all the little things that are just customized per board, and they're fairly obvious. And where'd it go? Here, yeah. So all of this stuff is include config.h. Every one of these config options is undefined in there with a very detailed text description of what it does and where it's used and why it's useful. And so if you're wondering what these features are, you can go and look at include config.h, and it will tell you. And it will also tell you some of the other things you might want to turn on. So that said, what are all these responsibilities of the EC anyway? Well, I've mentioned a bunch of them. Power sequencing, the AP, monitoring battery charging, making sure it works properly, keeping things cool, keyboards, various buttons and switches, LEDs, blinky lights, that sort of thing, and a few other peripherals that might be specific. And monitoring all that's what the EC does. Power sequencing then, and we'll look at some of the code that does that. Obviously each AP family has power states, voltage regulators, controls for those states and regulators, rules about timing and what happens when and what I have to do and when these things happen. And the EC has to handle all this. I wish it was as simple as just turning it on and off, but it's not. There's huge long tables of this power must be up and stable for 3 milliseconds before this power comes up, and then this signal should go high, and if it doesn't, you do this thing and then wait for it to go high. And so we have code that handles that. Here's an example for the Haswell chipset family. And this is one little snippet that you will find in the power haswell.c file, and it says, okay, here's a case where the AP is moving from the S5 state to the S3 state, which typically happens at boot. And so for this particular board, I have a 5-volt rail and I need to turn it on. So I will turn it on and then I'll wait for a while to see that it really came on. And if it didn't come on within some sane period of time, a second or two, then I force everything into shutdown. I say, oh, something's weird, it's not coming up. And then I say, great, all right, let's assume that came on. Now there's some other rails that should always be on when the 5-volt supply is on. Let's make sure they're on. Then we turn on the power to the memory and we wait for it to come up. And then finally, we got the memory up and everything. Now let's enable the touchpad. Now I'm coming into S3, which is still a suspended state, but the touchpad, if I touch it at this point, I might want to wake it on up into fully operational mode. So we turn the power on to the touchpad. And now, in order for the touchpad itself to say, whoa, I need to be ready to deliver interrupts if somebody wants them, we call a hook. And we say, hey, the chipset is starting up. And so somewhere in the touchpad logic, there would be a hook callback that says, oh, when the chipset's coming up, I need to turn on interrupts. And when it's going to sleep, I can turn them off because I don't care anymore. And then finally, once that's all done, we say, well, the next state then should be S3. So I'm awake, I'm not asleep, I'm not off, but I'm not fully operational yet. And then we sit there and wait for the next event to come along. So this is an example of the sort of a state machine that might be run by the power task. If you're working with a completely new chipset family, beyond Haswell, Bailey Bay or whatever, Broadwell, you would have to customize these things not only for the particular GPIOs, but also the rules. How long do you wait, and what signals are there, and how long, what do I do when nothing happens? Hopefully, most of you will be working with a reference board that we've done, so this is taken care of. We hope. Okay, I mentioned battery charging. Most of our Chromebooks use smart battery technology, which has been around for several years now, in which the battery has a little processor of its own, and the charger can respond to it. And so the battery tells the charger, I need this much voltage and current, please, and the charger's job is to hand it over. And in many situations, and the way that the smart battery stuff is designed, you just connect these two directly together over an I2C bus. One is the master, one is the slave. Battery's the master. In our case, we run that through the EC instead. And the reason is there are a few special cases that we want to deal with. For example, if you fully discharge one of these smart batteries, it will actually go to sleep and not talk to you anymore before it gets completely broken and dead, because draining it all the way down can damage it. And so the little controller on the battery will stop listening. So the way to wake it up is you give it some charge anyway and then see if that gets better. Well, if it won't ask, the charger won't do it, so we have to do it. So we might do that. We've also got the ability to force different charging curves. The battery knows how best to prolong its life, but we might want to say, hey, we can lose 2% of the battery life if we charge it twice as fast for the first 30 minutes or something like that. And that might be worthwhile doing. So we'll do that sort of thing if a particular OEM wants us to. And there may be errata in there where the battery's not quite right. We need to kind of massage some of the numbers it's asking for. Very similar. We also have, the EC has to be part of this because we want to make sure that all the temperatures are safe. Each of these batteries may have thermal limits as to if it's too cold, I shouldn't be discharging or shouldn't be charging or vice versa, things like that, or too hot. And then some of our Chromebooks actually don't have smart batteries, they have dumb batteries, and we have to do all this logic ourselves anyway, which is really, again, not that hard. It just means that the charging curves are part of the EC. And so you see here in each board we may have a battery.c that configures those parameters. Here's an example. It says what's the maximum voltage, the nominal, the minimum. And this will vary because some batteries may have all their cells in parallel or in series or in various combinations, and that needs to be known. And then again, temperature range, what's the pre-charge current, how much do I give it when it's asleep and not listening to me, what's the trickle charge current, things like that. And those vary from manufacturer as well as design. Okay, thermal management. We have a lot of temp sensors scattered all over these things. Some of them have just one or two, some have lots. Here you see some of the examples. I think this is from Link, or I'm sorry, the Pixel. And we have several different sensors hanging on the I2C. The ones that say not calibrated, these are kind of sensors where it measures the die temperature and it also looks up at the sky to see what the infrared readings are, and they have to be calibrated. And I was playing with this one, so it's not. And then we have the internal sensor on the embedded controller itself, as well as the PECI sensor that comes from the chip, from the AP. And so it tells us these are all the values that we've read. And then we can also set up various thresholds to say, for example, any particular sensor, number 1 through 9, which we just saw here, we can say when it reaches a certain threshold, we may want to warn the AP through an ACPI event, something like that. We may want to hit the high point where we need to throttle it by pulling a signal. We may have to say, you know, when it gets over this, I don't care what else is going on, we need to turn the system off because it's about to melt. And then related to that, we can set thresholds for when to turn the fans off and on. So we could say, all right, we want the fans to come on a little bit when the temperature gets above 30 degrees and maybe be at full by the time it's at 70 degrees on one of these sensors. And maybe a different sensor would say, well, if my temperature is 40 degrees, I need the fan coming on, even if the CPU is off. So we can set fan off and on thresholds as well as min-max for all these kinds of things. And that gives us a lot of flexibility because we can say, you know, cool parts of the chip even when other parts may or may not be as hot. And the fans themselves, of course, are kind of continuously variable. We have a hysteresis and so forth. And so we can control them there will be some minimal speed. It'll be off or it'll be running at a minimal speed. You can't run a fan down to 2 hertz. You have to, you know, there's got to be a minimal point. But within that range, of course, we kind of vary it continuously. And we think it works pretty well. I mean, obviously, the AP could drive this information if it's awake and if the CPU, if it's not in recovery mode or sitting there waiting for somebody, or in the BIOS where it's not telling it. So obviously, the EC has to do something in those cases. But we've had pretty good results just controlling the fan from the EC. Okay, keyboard. x86 system, we have a fairly standard, in some sense of the word, 8042 style keyboard interface, just like the old PC-AT had. And I say standard because there's about 100 different versions out in the world. The ARM-based systems, we use a binary format where we just push the whole keyboard scan matrix up to the AP and let it deal with it in the kernel driver. Either way, we have to customize the scan matrix to say in a particular board, for example, how long does it take after I notice a button being pushed before I can decide that it's stable? What's my debounce time? How often do I watch it once something happens? And again, there's a keyboard scan task. What happens is normally it's asleep. It's not doing anything. When I come along and poke a button, it gets an interrupt and it wakes up and then it watches the keyboard for a certain period of time and then says, okay, for example, here's a second. In this case, it would say, all right, after a second has elapsed and nobody's pressed any keys and there's nothing down, I can go back to sleep again until the interrupt happens again. So it's sort of a wake, poll, go to sleep model. Finally, of course, we have to model the keys themselves. In this example, we have a 13 by 8 scan matrix, and so we have to tell it which of those scan lines even are connected to things. And you can see not all bits are 1, so we don't have the full 104 keys. We have 75 or something. Okay. Of course, there are various other peripherals that the EC has to manage: LEDs, power charging lights, backlights, the light bar on the Pixel. There are some systems with accelerometers. There may be dedicated buttons as addition to the lid closes and things. Mostly these are board specific, and they can generally be handled by just a hook callback that sits around. You say in my board, hey, whenever somebody pushes this button, wake me up and I'll look at it. Or even better, once a second, see what's going on with the LED and update it if I need to change it. Okay, so far so good. So now you've seen some of the examples of the files that get changed. You've seen what they do. You've seen what the board-specific files on, and it would make a lot more sense when you just look at them. It's not rocket science at this point. This is clever and complicated and annoying. So what happens is we have both a read-only and read-write half of the firmware on the embedded controller, but the embedded controller is small and doesn't have a great deal of cryptographic processing capability, and even if it did, it takes longer because it's kind of small and perhaps weakly powered. So the way we make sure that the read-write firmware on the EC is correct and matches the read-write firmware or corresponds to the read-write firmware on the AP is when the system is completely cold off and the EC boots up. It boots up and it's running its read-only firmware. It powers on the AP, even if the lid is closed. And the AP then boots up its read-only firmware. The AP then, because it's doing a normal boot, it verifies its read-write firmware and jumps to it. Okay. Now, meanwhile, the EC, sitting in its read-only firmware, has computed a hash of the read-write firmware. It just scans the entire hash memory and says, the entire firmware memory for the read-write section, and says, this is my SHA-1 or whatever. Meanwhile, then the AP, in its BIOS firmware flash, it has a copy of the EC's read-write firmware, the one that it ought to match. And so the AP then says, all right, EC, what hash do you have? Says, my hash is 52. And the AP says, it should be 14, you're wrong. And so then the AP says, all right, EC, here, take this new firmware. And it shoves this new firmware down to the EC. EC programs its read-write flash and then jumps to it. All right? So the next time it boots, goes through this process, they'll both have the same hash. All right? And there's some other stuff that goes on just to be sure, again, like I mentioned, the Silego chip, so that the EC is not lying about whether it's in read-only or not, what the hash values are, that kind of stuff. A few other things involved. But this process happens every time the thing boots. And then let's say the lid's closed, everything says, all right, everybody's good, everything's good, let's go back to sleep. But now the EC is awake and running its read-write firmware, and it matches the firmware that it expects to see the next time the AP boots. Okay. So what happens when I'm writing my own EC and I'm working on code? Well, what happens is I make all these changes, I make all these edits, I finally get everything to compile properly, I program it, I boot it, I watch it come up, and it's like, nothing's changed. What happened to all my code? Well, the answer is it booted up the AP, said, that's not what you're supposed to have, and it shoves it back down, and all my changes went away again. Well, I wasted about an hour one day doing that, and I knew this was supposed to happen. So how do we fix it? There's a setting, there's a flag in the GBB. You remember we talked about the Google Blessed block or whatever it's called in the read-only flash. So you go to the AP's BIOS and you set this flag and you say, hey, stop that. Okay? And so you can set a flag to say, for example, here's an example. Boot really quickly, pretend you're in dev mode every time, make sure I can boot from USB if I want to. Don't worry about rollback checks because I'm changing version numbers and everything's version 1. And disable software sync. So whatever EC it has is the EC it gets, and then it's up to me to make sure I don't do something it doesn't expect. But that's really handy. And we actually have factory checks to make sure these flags are all 0 when it leaves the plant. But for development purposes, it's great. Okay, so, yeah. Yes, as was mentioned, you have to take out the write protect screw. You can't change anything in the GBB. It's part of the read-only firmware on the AP side unless write protect is disabled. And to do that, you have to open up the board and physically remove a screw or a jumper. So end users would not be able to do that without voiding their warranty. They can. We tell them how. It's all public. Okay, so you're going to start a new board. What do you do? Well, same as everybody else has mentioned, you start with a reference design or at least something that's recognizably similar to what you're working on. What I prefer to do is get one of those reference systems, build the firmware for it myself, put it on there, check some version strings, ask it some commands, make sure that it is the firmware that I just compiled and put on there. Now I know it works. Now we're going to work on the new system. Okay, so again, you create a new subdirectory in the board area, put your stuff in it, copy that stuff in, and now here's the tricky bit, just go through and disable everything that you can, right? If you know you're going to need certain features, it's fine to leave them commented out, but take it all out. And generally what I do is I start with the GPIOs because the embedded controller, generally you can boot the embedded controller fairly easily. What you can't do is get it to boot the AP properly. And so the first thing is stub out everything. Don't worry about I2C bus. Don't worry about LPC. Don't worry about this kind of stuff. Just stub out all the power sequencing even, unless you know it's working. And then turn on GPIOs one at a time and see, okay, I turned on this GPIO. Did the power rail come up? Read this other one. Does it tell me it came up? Good. Okay, now the next step. And so you're kind of going through the boot process one step at a time. And we will have done most of this on reference boards, but what we've seen with a few is we'll start with a reference board that has, say, 5 voltage regulators or something, and then one of the derivative boards may have 4 or 6 because we've combined some things or added an extra feature, and so, or maybe connected it to a different GPIO. And so this process can be a little slow and cautious until you know everything's up and working. And then, of course, you use the EC console to say, what GPIOs did I turn on? Are they really on? Can I shorten them with a probe and see that that happened? And then once that's happening, everything's booting, everything seems to be working, the AP's coming up, shutting down, doing all that, you can add additional modules, measure the fan speeds, control them, that sort of stuff, right? And again, compile, repeat, whatever. There's a few tools that we've mentioned throughout the day. Servo, which is a hardware debug board from us, connects to this debug port inside the Chromebook and then to USB onto your Linux desktop. Servo D is a little daemon that will talk to it and let you expose the serial ports and so forth nice and neatly. OpenOCD is a open source tool that lets you reprogram various parts through JTAG and other sorts of buses, which we use to program the EC. And then FlashROM, which will program the AP flash also through Servo, but as well it will also program the EC and AP from on the Chromebook itself. And let's see, I thought I had a picture on here. Nope, this is my old slide. Okay, so I had a picture of the servo board, but it's on a different set of slides, the one that you can see. And we will have some more documentation and so forth real soon now, within the next week, that kind of walk you through the whole process of building the EC and so forth. Questions? Still awake? Everybody there? Okay. That's it then. Hopefully all will become clear when you try it yourself. I had an example here. Here's the EC code. I'm in the source platform EC directory. And if I look under board, I see all the various boards. If I look at one, let's say board link, or here we can look at Ramby. Ramby's pretty good. Board.h. We see we have configured various features. We tell it what kind of charger it has, power button controls. We tell it, on which I2C ports are the battery, are the charger. Will we find certain thermal controls? How many ports are we using on the USB? What are my wireless signals to turn it off and on, enable the radios? Here's those special, here's some my normal inputs. Now I define all my GPIO inputs and outputs. I define classes of signals to tell me when the power is good or not. I have my ADC channels that tell me how many ADD converters I have, PWM controls for the fans and lights, sensor lists, so forth. All right, and then also in the corresponding C file, I say, okay, great, I got these GPIOs. What pins are they connected to, and what do they do? Here's my PWM information. My ADC information says, okay, I have a certain number of ADD converters that I'm using to measure current on the charger input. I have to convert it from whatever the ADC reading tells me to, milliamps or something like that. How do I do that? How do I control my PWM? Is it active, low, or high? And on what bus is it? Things like that. If I have temp sensors, where are they connected? What types are they? Where are the functions that know how to read them? What are my default thermal config parameters in terms of limits and things like that? And there are none, so we're still working on this. And then a couple extra things like that. You'll see other things in the board directory that have to do with our task list, blinking the LEDs, tweaks to the battery, like I said, to set the parameters and so forth. Fairly straightforward, not a lot in there, and not a lot to customize. So, okay, good. Yeah, there's one. Yes. How long? What? How much testing do you do before you submit a CL? All of it. There is, if you try to upload a code change to our tool, it will yell at you unless you have run make build all, so that we know you have built all of these boards. Here's the boards. This board. You have at least built all these boards. You have not broken any compilation errors. There is also a make run test that tests functionality of the EC logic, but it runs only on the build machine, so it emulates a lot of this behavior. So if you've broken something in terms of responding to events, it will tell you that. It won't necessarily tell you if you've broken something in one of these other boards, right? So for that, we have some automated tests as well as peer review and so forth that we have to look at. So yeah, test everything you can, upload the CL, the code review change list, and then we will look at it and ask questions or ask for clarifications, just like with anything else. Okay. Yep. Anything else? No? All right. Yeah, one more. Yes, we have a stack. There's a stack info command or task info command that tells us how much stack has been used up to this point. It's just a high water mark for each task, and how many times the task is run and so forth, interrupt counts, things like that. So the EC manages and monitors all that. Typically, we have stack size between 256 bytes and 640. We have not needed any more than that. Most of them run about 512 bytes, and they only consume 90% of that. So the biggest stack use, if you do get a stack overflow, there are some boundary checks that the task switcher makes every time there's a dead beef at the beginning and end of the stack to see if you've run over it and written it. And it will detect some stack overflows and things, and then throw all kinds of screaming fits when that happens. The only time we have seen that happen is when we've added a bunch of magic commands with a whole bunch of nested printfs, and so we print, and that all happens in a stack and it overflows. But we don't use that except for debugging. So, yep. Yes. I think we run the Blizzard at about 15 kilohertz, something like that. It can go much faster. It can go up in like the 50 megahertz range, but we don't need it 15, 16 kilohertz. So we run it really slowly, and I think the STM is even a little slower. There's really usually not much for it to do. Keyboard, battery, fans, that kind of stuff, it doesn't take a whole lot of time and effort. And a lot of that time, even at that clock speed, it's spent idle. So. No, that's it. It does go to sleep. I think I've mentioned this somewhere in one of the slides. If the machine is on battery power and the AP is off and it's just sitting there, after an hour the EC will go into hibernate mode because then you're not going to wake it up. If you haven't come back and opened the lid again in an hour, you're probably not going to, and so it's just going to go to sleep. So, yep. All right. Okay.
Thanks, Bill.
Yep.